In this course, we want to create a long short-term memory or LSTM network in Python from scratch. And if you want to start with this lecture and want to join me, you're going to need a few prerequisites. So for example, you should be fluent with basic OOP operations and, for example, methods, classes, and inheritance. And of course, we're going to need some linear algebra, dot products, the inner product, the outer product, in principle, how you multiply vectors and matrices. So we will use NP dot quite a lot. And of course, when it's about the method to optimize our loss function, we're going to use gradient descent. And therefore, you need to know how derivatives work. And especially when we talk about backpropagation and also backpropagation through time, it's very important that you're fluent with the derivatives, inner derivatives, outer derivatives, and so especially the chain rule. And what also helps a lot is if you have watched the other lecture, RNN from scratch, because we are going to use lots of the code from RNN from scratch. And we're actually going to start from a simple RNN cell and turn it into an LSTM cell. Nevertheless, I still want to show you during the course what an RNN cell looks like, and also want to repeat this a bit. And that leads us to the outline. So I want to explain the idea of an LSTM. So why do we need to modify our standard or classical RNN? And I want to explain, of course, how to do that and what the difference is. And then we have to take a look at the backpropagation through time, which will be a bit more tricky than in the case of a standard RNN cell, and will be a bit more complex, but I will also want to guide you through that step by step. Want to show you the math first, and then also how the math turns into code. And then, of course, we want to apply it and test it. And that's what we're going to do in the chapter I call full backpropagation. And then we want to use an optimizer that we have been programming already in the other courses. So we're just going to copy and paste the code, and then we modify it accordingly. And it will be a standard stochastic gradient descent optimizer. So the same optimizer we have used earlier. It will include learning rate decay and a momentum. Yeah, and then finally, of course, we want to put this all in a nice package where we can train the LSTM and also apply it to new data. And in particular, we want to test it and compare the result to the classic RNN that we had earlier. And you will see that actually it does make a difference. So first of all, what is the idea and where did it actually come from? So we still want to analyze time series and want to make prediction/forecasting. And you can actually use this for speech recognition or anomaly detection. For example, if something happens that is not in according to the prediction in the forecasting. And we kind of did it already with the RNN, and the classic RNN can actually do that. And I want to show you some results from the last course. So you see the data we used for training data, and then the prediction, and we could also predict the behavior of the data in the future, and it worked pretty well for data that had this kind of structure. However, if you have a long-term change, then it did not really perform well. However, I have to say, I didn't really play around a lot of the training parameters, so you definitely can do this in a much better way. But the point is, what we're going to build now will deal with these long-term and short-term changes quite a lot better. And that's the idea of an LSTM, and that's why it's called long short-term memory network. So we have a long-term and short-term memory, and it is will be able to distinguish between short and long-term events, and also will be able to learn them, of course. And it also will deal with the vanishing and exploding gradient, the problem we had for the classical RNN. And there are lots of benefits we can get from that. So it will be more stable. It will be also faster. And also you can apply it to more complex data. And it was invented in 1997, so like 25 years after the classic RNN, by Sepp Hochreiter and Jürgen Schmidhuber. And it was a PhD thesis, by the way, and was published then, and of course was very successful and has been used successfully. And that's the aim of our lectures, that we kind of rebuild such an LSTM. So we want to build a many-to-many LSTM and also a one-feature LSTM in order to keep the whole thing simple. But I will also show you how you can modify it if you want to turn it into many-feature LSTM. So, but we want to keep it simple again, so that you get the idea how it works in principle, so that you have something like a basic knowledge that you can use to improve, for example, your own LSTM, or that you can also understand the LSTMs you use, let's say from TensorFlow or something, when you use packages and external libraries. And you will see that when we have our LSTM and apply it to the same data set, it performs a lot better. And even after a few epochs, the fit will be really good. And also, if you apply it to more complex data, it's not always 100%. So it does not always provide the best solution, so to say. But you can really chinks it and really try to train it on more complex data. And even after a few epochs, it kind of gets the idea of the data already. So that's what I want to show in this little plot here. And also if you add more noise, and this is something you can really do once you have to code, play a bit of the LSTM, compare it to the RNN, to the classic RNN, and then you can really tell that it has improved the situation quite a lot. And the idea is still the same. So we have a vector in time, xt, and we want to predict yt in the future given on a new xt. So we still have a cell, and this cell connects x and y, and we want to apply the cell recursively over time so that it also propagates information from the previous time step to time step in the future. And of course, it has to learn which information is important. So there has to be something that we can kind of say that's context in quotes, of course. So it's still not like a language model, but there has to be something like a context if it learns between the short-term and the long-term differences and what is important, what is not important. So this is actually in an abstract sense already on the way of understanding context. And so we want to create a cell and want to apply it recursively in time. And we know already how to do that from the classic RNN. So if I talk about RNN, I really mean this kind of setup, not the LSTM in particular. So when I refer to RNN, I just mean what we had in the previous lecture. And here again is a scheme of the RNN cell. So we have our value xt, and we want to generate a value yt. And the idea is that we had a state vector ht that propagated the information or passed it on from the previous time step to a later time step. So that's how you kind of have a memory in the system because it learns how to keep information from the previous time steps and also pass it on to the time steps in the future. And the idea then is pretty simple. So we have two things that go in, so two inputs, x and h, and we just multiply this with a learnable. And we also want to have an output y, and we also multiply this with a learnable. So we just add the bias, like with a normal neural network. And of course, we have also activation function, like the tangents hyperbolicus that we use for compactification. So the idea now is that we keep our vector ht because we still want to have information that we pass on from the past to the future or to the current cell. But now we want to have a second strain, let's call it ct, that helps us to learn what we can remember and what we should forget, so that we have these two strains, and somehow these two strains have to communicate with each other and have to exchange information. But of course, the question is how to do that. And that's actually the key part of the LSTM. And of course, there's not the LSTM structure. So there are different structures and architectures out there, but they're more or less coming from the same idea, of course. And I will just stick to one particular architecture, which is pretty common. But if you look it up, you might see other platforms or other codes which are slightly different. But the key point is still that we have these two strains, and these two strains pass information from the previous time step to the first, to the next time step, and they have to communicate with each other because they have to say what is which part is responsible for long-term changes and which part is responsible for short-term changes. And I will explain this in more detail in the next chapter. So, but the idea is actually not very new. It's actually more than 100 years old. And I want to illustrate this also a bit with an example, which is an electrical circuit. So even if you don't know all the details about how an electrical circuit works, I just still want to describe this in a kind of more general way. So I hope you will get the idea. Don't worry about the details too much. And of course, you can always look it up if you like. But I hope you get the overall idea. So just imagine we have an electrical circuit and there's a resistance in between. And the resistance is usually called R. And so the current flows from plus to minus. So that's, of course, not the actual physical current. It goes from minus to plus. The technical current, so to say, goes from plus to minus. So just imagine you have the current that just goes from plus to minus and has to pass the resistant. So if you have a constant direct current, so to say, that doesn't really change a lot. However, what is interesting is actually if you have alternating current with a certain frequency omega. So that's the equation for that. Don't worry too much about it, but just think about it just goes up and down with a certain frequency. So you have the alternating current. And now let's think about a circuit and add some other resistance. So you can have a coil and you can also have a capacitor. And if you do the math, you can calculate the resistance. And what is interesting is that the resistance depends on the frequency of the current. Don't worry too much about how you can derive these equations. You can actually do this based on the Maxwell equations if you want to Google that. But for now, it's actually not important how you come up with these equations. What is important, however, is how the resistance of the coil and the capacitor depends on the frequency of the current. So for example, if we go to the capacitor, the resistance goes 1 over the frequency. So what does it mean? So if the frequency is high, the resistance goes down and gets lower. So therefore, high frequency signals can pass this part in the electrical circuit through the capacitor easily because the resistance is low. If the frequency is low, so we have long-term changes, then the resistance goes up. So for example, if the frequency is 0, then you have just direct current that's just constant. So the frequency is 0, so the resistance is infinity. That makes sense because that's what a capacitor implies. There's the gap in between, so there's no flow going from plus to minus. So this passes short-term changes, but it blocks long-term changes because then the resistance is high. If you take a look at the resistance of the coil, it goes with the frequency, but it goes with the frequency proportional. So there are all these different constants, C and L. Don't worry too much about them. But the thing is that RL, so the resistance of the coil, goes with W. It goes with omega. So if omega is 0, so if there are long-term changes, those low frequencies, the resistance is also 0. If the frequency is high, the resistance goes up. So for short-term changes, they would actually go this direction through the capacitor. Long-term changes would prefer to go through the coil. So you have two passages or two gates. One, that's the one with the capacitor, passes short-term changes. the one gate with the coil passes long-term changes. And now let's imagine that those constant values C and L, so they're just, again, values you can calculate, but they're constant. Just imagine those values weren't constant and there would be learnables. Then you can actually train the circuit when to pass what. And that's the idea of the LSTM. And people actually in the past did quite a lot of the circuits because just imagine you have those parallel circuits with the 3 different resistance subsequently or in parallel. So you can just extract information from different frequencies from a signal. So you can really, for example, do a Fourier analysis of a signal, something like that. And this idea is pretty old. So people have been doing this for more than a century at least. So we have these 2 gates. The one passes short-term and the other long-term changes. And by the way, if you want to calculate the total resistance in this particular circuit, then you have this equation and then you can plug in the numbers. And then you can really see, for example, when the resistance is 0 and so on and so on. If you're interested, really, please look it up. You can actually learn quite a lot. So that's first of all the idea with how you can in principle understand the idea. So you have these 2 strains and they have to communicate with each other, but you need to have at least 2 different gates. So you have a gate for short-term changes and also a gate for long-term changes. And somehow you have to remember what is important long-term and what is important short-term. So for example, if there's noise and we will add some noise to the data, this is something which is not worth to remember because it's random noise. You can't predict that. So this should be something where the network should learn. It can actually forget about the noise because it's random, it's not predictable. So that's the idea. So that we have this communication between the different strains, so H and C. And now let's try to understand how to connect them with each other. So we have these different strains and they have to be connected. One idea is actually, if we want to pass information from H to C, we can actually do this with a sigmoid function so that we pass the information through a sigmoid function. Because as you remember, the sigmoid function maps values from minus to plus infinity to 0 plus 1. So for example, if you add an information after it passed the sigmoid, you will add, for example, 0. If you learned it's not important, you will add with plus 1, multiplied with plus 1, so to say, and then you will add the information because it's important. However, you can also multiply with the sigmoid, because that means then, for example, if you multiply this with 1, you keep the information exactly as it is. You don't change the information. If you multiply this with 0, then you delete the information. And that actually will be a key point. And we also want to keep control over all these values. So we also want to use a tangent hyperbolicus function just for compactification, as we did earlier as well. And so we will use these activation functions. And of course, now we have to add learnables as well, so that the network learns which information has to be passed on, which information is important, which information is not important. Well, and I will explain the details in the next chapter, where we really want to see, where we really gonna see how to turn our RNN cell into an LSTM based on the idea I just explained.